previously we had looked at elements. We're talking about pure substance and we're subdividing it, and we looked at elements in your last class. And we saw that elements could be subdivided more further into the metals, the nonmetals, and the metalloids. Right now we're going to now focus on compounds. So if something is a compound, it still fits under the category of being a pure substance, but it's not an element. So let's see what a compound is. If you've ever looked closely at table salt, you'd see little bitty crystals that are shaped like cubes. And these cubes are cubes because of the arrangement of the things, the atoms, the ions that make it up. So here is the definition of a compound. You have to have two or more types of atoms, and those atoms have got to be in a very fixed ratio and have to be of uniform composition throughout. And it cannot be easily separated into pure substances. So let me point out some very key bits of information we see in here. Okay, two or more types of atoms. Okay, so what we mean here is we've got more than one type of element in a fixed ratio. So I could take maybe some gold symbol is AU, and I could take some silver, AG, and I could melt them and stir them up and have a lot of gold and a little silver and a lot of silver and a little gold. That wouldn't make a compound. In a compound, there has to be a fixed ratio. So we see that in this structure here. We see that there is, for every Na, which is the orange, there is a Cl, okay? So there's a pairing, and it all ends up being, for every Na, there is a Cl. And it also says that it cannot easily be separated into their pure elements. It's difficult to separate them from each other and get pure Na and get pure Cl separate. It's a very difficult process. It's a big chemical process. You can't just separate them out using some kind of physical technique. It's got to be a chemical technique. We'll talk more about physical versus chemical as we move on. So right now that's kind of a complex thing for me to say. So we'll just keep it this way. It cannot easily be separated into their pure elements. So compounds, usually when they form, undergo a big change in energy. And it's generally a lot of energy being given off, an evolution of energy. And we see a flask here that's being represented as a bright flash. What's happening in this flask is a reaction to make a compound from its pure elements. Now, what's really important for us to understand is that the compound has no properties whatsoever like the elements that make them up. So if you make a compound, for example, let's think of the compound, let's write on the board here. Let's think about the compound water. We're all familiar with water, and almost everybody comes into it with the knowledge that H2O is the formula of water. This would be a compound. It has a fixed ratio. You have to have 2 hydrogens for every oxygen. So that's a compound of water. It is made up of hydrogen, and hydrogen as an element is actually diatomic, it's H2, and it's made up of oxygen, O2. Now the properties of hydrogen are nothing like what water is. The property of oxygen is nothing like water is. These two things are gases, okay? They're gases. We use oxygen and it's in the air that we breathe. And this is a substance that, if it's with the presence of oxygen, can blow up really fast. So there's this big release of energy, as we said in the picture there. You've got a big release of energy to make water. Now you know that water is not a gas, typically. It is a liquid. We drink it. It is not harmful to us at all. If you get too much oxygen at once, it's harmful to us. Hydrogen, you would not want to breathe it in whatsoever. Okay, so they have very, very different properties than the compound that makes it up. Now what we're seeing in this flask is actually, and we see in the image there, the third flask is this reaction taking place. What they've done is taken some sodium metal. And sodium metal, its formula is Na, is a very, very soft metal. You can cut it with a knife. It's very, very reactive. You wouldn't want to hold it in your hand. But you can take that and you can put it into a flask that has some chlorine gas. Now, chlorine gas is actually a diatomic molecule again, and we see that being represented in the image up here, these little diatomic molecules. That chlorine gas is in the flask, and as soon as it hits that flask, you're going to get this big flash. And that's the reaction taking place here at this flash. So now we've got sodium chloride. Now, sodium chloride is table salt. In its tiny little cubes of sodium chloride, it has no color. We say it's white, but in chemistry and in the sciences, we call it colorless. And it's not going to be harmful to you unless you consume way too much and you've got high blood pressure. So you sprinkle it on your French fries, you eat it. It makes your food taste better. This is, you know, we'll put a smiley face. We don't have any problem with this. Chlorine gas would be very, 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 very dangerous to inhale. It would cause extreme damage to your lungs. This, I told you, you wouldn't want to hold in your hand because it's very reactive. It would react with the water and burn you quite rapidly. So you don't want to be around and touch, and you had to be very careful with those two things. But heck, sodium chloride is great. So you have got to keep in mind that when you have a compound, it is nothing like the elements that make it up. All right, let's move on here. Chemical formulas for compounds. So the chemical formula is the way you represent it. If we look back here again at the board, we've got the formulas being written here. Okay, so we've got formula for hydrogen, we've got a formula for oxygen, we've got a formula for water. This is going to show what atoms make up the substance and its ratio. So for a compound, you know, I've got a compound of water, it has 2 hydrogens for every oxygen. On the screen, we see ammonia being represented, and I'll write that on the light board here. Ammonia, which has 1 nitrogen and 3 hydrogens. We see that fixed ratio taking place in here when we write that formula. So it has to show all the elements and their fixed ratios of that make up that compound. The top picture that we see on the screen now is the sodium chloride. Now, sodium chloride is a large 3-dimensional molecule that's, or I'll use molecule in quotes. It is a compound that is big enough, and so many NAs and so many Cls, so in this picture the NAs are purple and the Cls are green. There's so many of them that it's large enough for us to actually see. Now, you may not have any concept of what that is, but that is more than billions and billions if it's big enough for us to see. But when we write the formula, we write the smallest whole number ratio of those, so we would only write it as NaCl because we wouldn't want to have to write it as in this substance there's Na 5,463,742,142 sodiums and that many, I'm not going to try to write it all, boom, 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 chlorides. Okay, we wouldn't want to write all of that out. What we would want to be able to do is just whittle it down to the smallest whole number ratio. Oops, wrong direction. NH3 is actually what we call a molecule, and it's a small bundle of atoms, 1 nitrogen and 3 hydrogens in that little bundle there. Okay, so we have done our subdivision. We had our pure substances at the top, okay, if we think about our flow chart. We came down and we had the elements on one side and the compounds on the other side. We looked at the elements kind of closely before, and now we're looking at the compounds. We're going to learn that compounds can be further subdivided into different types of compounds as we proceed on. All right, so that's just the flow chart that we were mentioning with the compounds. So don't think that there's not a bunch of subdivisions under here, because there will be a lot of ways to subdivide that out eventually. Now, a little bit about compounds is the term molecules, but molecules does not have to apply only to compounds. So let's get we've got a difference between elements and compounds. Elements are made up of all the same atom, and compounds are made up of more than one type of atom or more than one type of element in a fixed ratio. What molecules are does not apply to the term element or compounds exclusively. You can talk about molecules for elements, and you can talk about molecules for compounds. Now, if we look at our picture up here again, this is an element, because it's made up of all the same type of atom, hydrogen. and it is a molecule. It's made up of 2 atoms. This is oxygen. It is an element because it's made up of just oxygen atoms. So this is an element. But it is a molecule of oxygen because it has 2 atoms in it. This is a compound because it's made up of more than 1 element in a fixed ratio. And we're showing this formula as a molecule, and this actually is a molecule where we have 1 oxygen and 2 hydrogens attached together. Okay, so it says a collection of relatively small number. This is 2, this is 2, this is 3. A relatively small number of atoms that are held strongly together, bound strongly together. And we'll learn about those bonds, what's holding them together as we proceed with this unit. So if you were to take this water and you were to melt it, no, it's already melted. You were to freeze it or you were to boil it, go in either direction. Let's say it's a liquid right now, so I'm going to put an L after it. If it's a liquid. If I were to boil it, it would stay intact. Okay? If I were to freeze it, it would stay intact. And now I put an S because it's a solid. So it keeps its bonds, whether or not you heat it and boil it, whether you freeze it, whether it's a solid and you melt it, it keeps those bonds intact if it's a good molecule. So here on the screen, and we'll turn our attention to the screen here, we've got examples of some molecules that are what we call diatomic. What does di mean? It means 2. So it has 2 atoms in it. So we have 2 atoms of oxygen, we have 2 atoms of nitrogen, that's diatomic. Now both of these are examples of elements. This has also got 2 atoms, but is this an element? No, it's a compound. Okay, we have more than 1 type of element in it. Now here I have what we use the word poly, which means many. Polyatomic. And we've got phosphorus. Now, is that an element or a compound? Let's think about that for each of these. Which is it? Is it an element or a compound? Well, it's an element because it's all the same atom. Water's a compound. How about carbon dioxide? Is it an element or is it a compound? Well, since it consists of carbon and 2 oxygens, that's different elements, so this would be a compound. So the term molecule applies to a small bundle of atoms that are tightly bound together, but it can apply to elements or it can apply to compounds. All right, so this completes our lesson about the dividing. We're trying to go through how to classify matter. We have classified things as being pure substances to begin with. Now there's another type of thing, and that's mixtures. You're going to read about mixtures. Okay, so make sure you do that. Compounds versus, element, I've got to do it again. We've got pure substances versus mixtures. We'll talk about mixtures and you'll read about mixtures later. The pure substances are divided into elements and compounds. The elements were divided into metals, nonmetals, and metalloids. The compounds we haven't subdivided yet, but we will.